Today we'll discuss about the nature of names and special words in programming languages, and we'll be also discussing about the attributes of variables, including their type, address, and value. All this, and we'll be discussing about issues of aliases, etc. So as we discussed earlier, imperative programming languages are abstractions of the underlying von Neumann computer architecture. So the architecture's two primary components are its memory, which stores both instructions and data, and its processor, which provides operations for modifying the contents of this memory. Okay. So the abstractions in a language for the memory cells of the machine are variables. Okay, so the memory cells are accessed through these variables. So you can say that these variables are abstractions in a language for these memory cells. You can call it as an abstraction. So the characteristics of the abstractions are very close to the characteristics of the cells. For example, this is an integer variable which is usually represented directly in one or more bytes of memory. So in some cases, the abstractions are far removed from the organization of the hardware memory, as with a three-dimensional array, which requires a software mapping function to support this abstraction. So we know that if we have multi-dimensional arrays that can be represented in row major or column major format. And a variable can be characterized by a collection of properties or attributes. And the most important characteristic is its type. And that is actually a fundamental concept in programming languages. So designing the data types of a language requires that a variety of issues be considered. And among these issues, the most important are the scope and lifetime of variables. Okay, the scope and lifetime of these variables. And in the case of functional programming languages, they allow expressions to be named. So these named expressions appear like assignments to variable names in imperative languages, but are fundamentally different in that they cannot be changed. So they are like the named constants of the imperative languages. And in the case of pure functional languages, okay, they do not have variables that are like those of the imperative languages. So however, we can say in many functional languages do include such variables. Okay, so we'll be discussing about what is meant by these variables, their value, type, etc., their address, even what is meant by aliasing, etc. So we'll begin our discussion with this names. So the term, this name means that the term identifier is often used interchangeably with name. So names are also associated with subprograms, formal parameters, and other program constructs. Okay. So the term identifier is used interchangeably with name. Okay. So we'll use name or we can use identifier. And the main design issues with these names. Okay. So the following are the primary design issues of names. So are names case sensitive? You are mainly familiar with these kind of issues. Okay. Are the special words of the language reserved words or keywords? Okay. So we'll look at name forms. Okay, so a name is a string of characters used to identify some entity in a program. Okay, so as we know, for example, area. So that is a name and it is a string of characters and it is used to identify some entity. Okay, and we'll see what is or the notion of these names in different languages. For example, like Fortran 95 plus allows up to 31 characters in its names. C99 has no length limitation on its internal names, but only the first 63 are significant. Okay. Then external names in C99. External names means those defined outside functions, which must be handled by the linker. These external names are restricted to 31 characters. And names in Java, C#, and Ada have no length limit. And all characters in them are significant. We know the case of C99, they are not giving any restriction for the length of this names, but only first 63 characters are significant. But that problem is not there with this Java, C#, and also C++ does not specify a length limit on names, although implementers sometimes do. Implementers. So the programmers sometimes restrict the names, but C++ actually does not specify a length limit. And names in most programming languages have the same form. Okay, that is a letter followed by a string consisting of letters, digits, and underscore characters to form names. Okay, so in the and we know that these underscore characters, so we started using them in 1970s and 1980s. And in the C-based languages, it has to a large extent been replaced by the so-called camel notation. So in which all of the words of a multiple word name except the first are capitalized, as in my stack. Okay, so that's what it is, a camel notation. So we can somehow we can replace the usage of underscores. That is, in C-based languages, the notation or their notion is that a multi-word name. So we'll see different names in a multi-word name, and we'll capitalize those multi-words except the first one. Okay, and the use of underscores and mixed case in names is a programming style issue. Okay, not a language design issue. Okay, so the programming style issue is this mixing up of this cases and underscores. Okay, and all variables in PHP must begin with a $sign. And in Perl, the special character at the beginning of a variable's name, that is dollar, then at the rate or this percentage, specifies its type, although in a different sense than in other languages. Okay, and in Ruby, special characters at the beginning of a variable's name, that is like ampersand or double ampersand, indicate that the variable is an instance or a class variable respectively. Okay, if we are using at the rate, means it is an instance, Double ampersand means it is a class variable. And in many languages, notably the C-based languages, uppercase and lowercase letters in names are distinct. Okay, that is, names in these languages are case sensitive. So, for example, the following three names are distinct in C++. Okay, see then, rose, rose and rose. Three roses, but the first one all small letters, second one all capital letters, and third one, the first is capital, remaining small letters. Okay. So for some people, this is a serious problem to readability, because names that look very similar in fact denote different entities. So in that case sensitivity violates the design principle that language constructs that look similar should have similar meanings. But in languages whose variable names are case sensitive, so although this rows and small rows look similar, there is no connection between them. Okay, if they look same means um, they won't be the same. Okay. And obviously, not everyone agrees that case sensitivity is bad for names. Okay. So in C, the problems of case sensitivity are avoided by the convention that variable names do not include uppercase letters. So they are not. So in C language, okay. So variable names do not include uppercase letters. In Java and C#, the problem cannot be escaped because many of the predefined names include both uppercase and lowercase letters, as you know. Okay, in Java, that is a usual practice. So we can consider, for example, the Java method for converting a string to an integer value is, what is it? ParseInt. Okay. So, and spellings such as PARSE, capital INT. Okay, and all small letters are not recognized. Okay. So our specialty is that the first P, that is pass, P for that pass must be small, and I should be I for int, that should be capital. Okay. That is one example. Okay. So we can have both uppercase and lowercase letters in languages like Java and C#. And next we will see what is meant by special words. Okay. As you know, special words in programming languages are used to make programs more readable by naming actions to be performed. Okay. They are also used to separate the syntactic parts of statements and programs. So in most languages, special words are classified as reserved words, which means they cannot be redefined by programmers. But in some, they are only keywords, which means they can be redefined. Okay, so you can have different notions for special words. That is, you have as reserved words, or they can be keywords. In the case of reserved words, it means that they cannot be redefined. But if it is keyword, then that can be redefined. So a keyword is a word of a programming language that is special only in certain contexts. Okay. Fortran is the only remaining widely used language whose special words are keywords. That is, in Fortran, the word integer Okay. So when found at the beginning of a statement and followed by a name is considered a keyword that indicates the statement is a declarative statement. Okay. So if we see the word integer at the beginning of a statement and that is followed by a name, that is considered as, a keyword that indicates a statement in a declarative statement. Okay. However, if the word integer is followed by the assignment operator, okay, and it is considered as a variable name. Okay. So for example, we have integer apple and integer equal to 4. And in the case of Fortran compilers and people reading Fortran programs must distinguish between names and special words by context. So a reserved word is a special word of a programming language that cannot be used as a name. And as a language design choice, reserved words are better than keywords because the ability to redefine keywords can be confusing. Okay, so that's what we say. Reserved words are better than keywords. The problem with the keywords is that we can redefine keywords. So there will be problem of, or there will be some confusions for the programmer. Okay, so it is better to have reserved words than keywords. That's what we say. So consider in Fortran, one could have the following statements: integer real and a real integer. Okay, so where this integer is a keyword only. So we can use it as, or you can redefine it. Okay, these statements declare the programming variable real to be of integer type and the variable integer to be real type. So in addition to this, the strange appearance of these declaration statements, the appearance of real and integer as variable names elsewhere in the program could be misleading to program readers. So there is one potential problem with reserved words. So that is if the language includes a large number of reserved words. Okay. Then the user may have difficulty making up names that are not reserved. Okay. So the best example of this is COBOL, which has 300 reserved words. Okay. So unfortunately, some of the most commonly chosen names by programmers are in the list of reserved words. For example, length, bottom, destination, and count. So in most languages, names that are defined in other program units such as Java packages and C and C++ libraries can be made visible to a program. And these names are predefined but visible only if explicitly imported. And once imported, they cannot be redefined. Okay, even though they are in the library, if we import them, then that cannot be redefined. Okay. Now we'll look at what is meant by this variables. So a program variable is an abstraction of a computer memory cell or collection of cells. Okay. And programmers often think of variable names as names for memory locations, but there is much more to a variable than just a name. Okay. So the move from machine languages to assembly languages was largely one of replacing absolute numeric memory addresses for data with names, making programs far more readable and therefore easier to write and maintain. So we have the machine languages and we moved from there to assembly languages. Okay. So what happened that time? We could replace these absolute numeric memory addresses for data with names. Okay. So in the case of machine languages, we had to use the absolute numeric memory addresses for data. Now we are able to use this names as memory addresses. Okay, that is actually abstractions of this memory addresses. Okay, so that actually makes it very readable and therefore easier to write and maintain. That step also provided an escape from the problem of manual absolute addressing, because the translator that converted the names to actual addresses also choose those addresses. So that time the human has to think like a computer or machine. So a variable can be characterized as a 6-tuple of attributes. So that is name, address, value, type, lifetime and scope. Okay, so variable has these attributes. So even though they look very complicated, it's a very simple concept. It provides the clearest way to explain the various aspects of variables. So as we know, the variable has a name. Name is an attribute of this variables. Okay. So these variable names are most common names in programs. Okay. So next one is address. So a name means that is a variable name. So an address. The address of a variable is the machine memory address with which it is associated. Okay. So it will have a machine memory address with which it is associated, and that is known as the address of a variable. And this association is not as simple as it may at first appear. Okay. In many languages, it is possible for the same variable to be associated with different addresses at different times in the program. Okay. That makes it very complicated. For example, if a subprogram has a local variable that is allocated from the runtime stack when the subprogram is called. So different calls may result in that variable having different addresses. Okay, so if we have a subprogram that has a local variable associated with it, but that is allocated from the runtime stack when the subprogram is called. So when we call it, or when we call this function multiple times, that will be mapped to different memory addresses. Okay, so these are in a sense different instantiations of the same variable. So the address of a variable is sometimes called its L value, because the address is what is required when the name of a variable appears in the left side of an assignment. And it is possible to have multiple variables that have the same address. When more than one variable name can be used to access the same memory location, the variables are called aliases. Okay, so aliasing is a hindrance to readability, because it allows a variable to have its value changed by an assignment to a different variable. Okay, so we have two variables and one memory, that is they are mapped to the same memory location. So when one variable, or when we give an assignment to one variable, that will change value of a different variable. Okay. That is the problem with aliases. So we see, let's see one example. If variables are named total and sum are aliases. So any change to the value of total also changes the value of sum and vice versa. Okay. So a reader of the program must always remember that total and sum are different names for the same memory cell. That is the only solution for this problem. So the reader must be aware of this, or a reader must always remember about this. Okay, because there can be any number of aliases in a program, and this may be very difficult in practice. Aliasing also makes program verification more difficult. And aliases can be created in programs in several different ways. And one common way in C++ and C is with their union types. And two pointer variables are aliases when they point to the same memory location. So the same is true for reference variables. And this kind of aliasing is simply a side effect of the nature of pointers and references. Okay, this kind of a aliasing is actually a side effect of this pointers and references. And when a C++ pointer is set to point to a named variable, the pointer when dereferenced and the variable names are aliases. So that is when a C++ pointer is set to point at a named variable. Okay. So that time the pointer when dereferenced and the variable's name, these two are aliases because they both reference to the same object. So now we look at the type, that is another attribute of variable. So the type of a variable determines the range of values the variable can store and the set of operations that are defined for values of the type. So for example, the int type in Java specifies a value range of these range. Okay. And arithmetic operations for addition, subtraction, multiplication, division and modulus. All these are allowed for this integer data type. And we have value. So the value of a variable is the contents of memory cell or cells associated with the variable. So it is convenient to think of computer memory in terms of abstract cells rather than physical cells. Okay. The physical cells are individually addressable units of most contemporary computer memories are byte size, with a byte usually being 8 bits in length. So this size is too small for most program variables. So an abstract memory cell has the size required by the variable with which it is associated. Is for example, the floating point values may occupy 4 physical bytes in a particular implementation of a particular language. A floating point value is thought of as occupying a single abstract memory cell. Usually we follow this kind of a notation or definition. Okay, so we always think about an abstract memory cell, though the physical memory representation for physical cell will be more than that. Okay. So the value of each symbol non-structured type is considered to occupy a single abstract cell. So henceforth the term memory cell means abstract memory cell. And a variable's value is sometimes called as its R value. Okay, address is L value. It is a value or value is called the R value because it is what is required when the name of the variable appears in the right side of an assignment statement. Okay. So to access the R value, the L value must be defined first. Okay. So such determinations are not always simple. Okay. So these are the main attributes of variables.